Now that we have talked about limits of multivariable functions, we can start talking about the continuity of such functions. So let us first look at what continuity means in single variable functions, and let's extend that to multivariable functions. So a graph is continuous if there are no breaks, as simple as that. So uh, to be more mathematical, we would say that y equals f of x is continuous. It would be continuous at x naught, y naught. So let's say this point right here, x naught, comma, y naught, if the following three properties are satisfied. Number one, that f of x naught is defined, and it's obvious, since if it's not defined, it's not going to exist anyway. Second, that the limit as x tends to 0 of f of x naught is also defined, and third, that the two expressions that you have in 1 and 2, they both are equal. So f of x naught is equal to, there was f of x, so f of x naught is equal to limit as x goes to x naught of f of x. Now, the best way to actually have to observe continuity is to be plotting a graph and checking whether things go right. However, there are some instances wherein you can't plot a graph, and multivariable functions are a perfect example of it. So instead of looking at just single variables, let's make it a bit more exciting. Let's have some multivariable function. So again, let's assume any general sheet function, any sheet, any function. It doesn't really need to be something really well defined, right, for the purposes of this discussion. And let's say we take a point x naught, y naught, and we find the value of that point, its image, on the curve, and let's say that is z naught. So in this case f of xy would be continuous at x naught, y naught if number one f of x naught, y naught is defined, so again, and number two, limit as x comma y approaches x naught, y naught of f of xy is also defined, and once you have found that they two are defined, you check whether the two things are equal. And if the function satisfies this property, for a certain point, then we say that it's continuous out there. Now, we can extend continuity from it being defined at a single point to it being defined over a region of points. So let's say that if you want to prove that the function is continuous for the entire real number set of x's and y's, you just prove that these three properties hold for all x's and y's that you take, and then you will just prove that the f of xy is continuous everywhere. You can have instances where the function is just continuous at some portions of the reals number set as well. So let's say an example of that. So if you have the function natural log or ln of xyz, this is a function that's dependent on three variables, so you're not going to be able to plot it, at least by the science we have right now. And what you can instead do is you can look at what places is this function even defined. and the places it's defined is when x, y, z are greater than 0. Because for any numbers equal to 0 or less than 0, the natural log just doesn't make any sense. There, you don't get a perfect answer. You don't get a real number answer. So basically, only the points that satisfy this equation x, y, z greater than 0 are the points for which the function's graph in 4 dimensions could have been a continuous graph. Let's look at an example of disproving continuity. So let's say you had a piecewise defined function, and it's defined as 2x squared y over x to the power 4 plus y squared when x and y are not equal to the origin, and it's equal to 0, simply equal to 0 if x and y are at the origin. Now, in a graph like this, firstly you check whether I am going to disprove. I forgot to state the problem. So the problem is that I have to prove, or you have to prove, that this function f is discontinuous. So discontinuous just means not continuous. Is discontinuous at the origin. So let's start by checking number 1. So number 1, f of 0, 0. We know that we have defined the function that way. It's equal to 0. 0 is a well-defined number, so check. Number 2, limit as x, y approaches 0, 0 of 2x squared plus y to the power 4 plus x to the power 4 plus y squared. Again, I just jumbled up the terms. And you have to prove that this is defined, that is, it doesn't have an indeterminate value, or it doesn't have a non-real number value, to be exact. So what you can do is you can try smashing your heads again, but as I said, in limits, when you see an expression like this, it's most likely that the limit won't exist due to different paths of approach. If you don't know about paths of approach, just review the previous video in this series. And what path of approach you can take is y equals kx squared. And if you plug that in, you get 2x squared times kx squared over x to the power 4 plus kx squared, and that would be equal to 2k times x to the power 4 over x to the power 4 plus k squared x to the power 4, and x to the power 4 can be cancelled out from this expression, and you would be left with 2k over 1 plus k squared. So depending on different paths of approach, you can take k to be equal to 1, you would get the limit to be 1. If you take k to be equal to -1, you get the limit to be equal to -1. So if you prove that the path of approach changes the value of the limit just doesn't exist. So since this doesn't exist, you don't need to check for the third case. You have already proven that the function is discontinuous. We can do one more problem. Let's try proving that the function e to the power of x plus z over 2 cos y, this 3-variable function, is continuous at the origin 0, 0, 0. So again, this is a function that you can't plot, so you will have to do something analytically. You can't really draw this function. So first, let's plug this number right in. So e to the power 0 plus 0, every variable is just changed by 0, so 2 cos 0, and you arrive at 1 over 2. So that's a good number, that's a well-defined number. Let's try taking the limit. Taking the limit as x, y, z approach the origin of this function. And basically, since since plugging in doesn't result in an indeterminate number, you just have the same value. You just have the same value. It's a defined value. It's a well-defined value. And again, so since both are same, you just arrive at, yes, the function is continuous. So this is continuous at the origin. Now, most of the functions that we will encounter for the purpose of simplifying our discussions further in multivariable calculus, we will assume them to be continuous, as to have various nice properties of differentiability or being able to take the integrals of that's called the integrability. And I really mispronounce that all the time. And so in all those cases, we generally assume that the function's continuous, and you will find functions that are discontinuous, but usually in life, our life is usually surrounded by functions that are continuous. But even knowing those special interesting cases where multivariable functions aren't continuous is a real lot of fun. So that's it for limits and continuity. We will meet in the next video and we will start talking about differentiation.